Hello everyone, this is Dr. Webb. In this video we're going to look at one of the most surprising theorems, and if you keep going on and studying math, Green's theorem actually turns out to be incredibly important in a number of places. So before we jump into it though, we need to put in some new terms. Because Green's theorem is talking about line integrals for closed curves. So, so first of all, we're going to say that a curve is simple if it doesn't cross itself between its endpoints. So a simple curve never crosses back over itself. So that is a simple curve. However, something with a loop in it where it crosses itself, that's bad because of this point where it crosses itself. A curve that touches itself on its endpoint so it meets back up, that's okay. But it can't go back through, meet with itself, and then loop back around. That's bad. Okay, so it's only allowed to touch itself at the endpoints. Okay, a close is curved if the beginning and endpoints coincide, so if it makes a loop, we saw that before, so that's closed curve. That is not a closed curve. That's not a closed curve. Even though it has a loop in it, it's not a closed curve because the two endpoints don't meet up, so that's not closed either. So to be closed, it needs to come all the way around and meet right at the ends. And then if we have a simple closed curve, so simple closed means it's closed and doesn't cross itself anywhere as it's closing. We're going to say that it's positively oriented if you go around it counterclockwise. So there is a simple closed curve. Positive orientation is counterclockwise. So same way as we think about radians, theta moving in terms of radians, theta goes in a positive direction. Okay, so if F is a continuous vector field and C is a simple closed piecewise smooth curve, and so C is our simple closed smooth curve in positive orientation, then to denote the line integral on C of F, we're going to put this little circle in the integral. And so that's being used to denote that this is for a closed curve. So this circle here is reserved for closed curves. And so that's mainly just when you use it in the notation, so whoever's looking at it, they recognize that the curve that you're looking at is closed. Okay, so let's do an example. Really integrating over closed curves is not different than anything else. So here we're integrating our vector field is x squared, comma x plus y, and we're going to integrate over a triangle with vertices 0, 0, 2, 0, and 0, 3 that's oriented positively. So let's draw out this triangle. So it has vertices at 0, 0, 0, 2, 2, 0, and 3, 0. And so there is our curve. So it does have 3 corners. So this is piecewise smooth. It's not smooth because of the corners, but it is piecewise smooth. It has 3 smooth pieces put together. So to integrate on this, we're going to need to break this up into 3 separate pieces. One for the bottom, one for going up along the side, and one for going straight down. Okay. And so then we're going to parameterize each one. So C1 is going on the x-axis, and so C1 we can think of as being just t comma 0, where t is going from 0 to 2. C3, well, that's going along the y-axis, And so we can think about this as being, well, if you notice here though, it's starting at 3 and going down to 0. And so I think I'm going to represent this as being 3 minus t, with my t's here going from 0 to 3. And so this will force it to start at 3, and then as t increases, it brings me down. And then for the last one, we're starting at 2, at 2, 0, and we want to end at 0, at 0, 3. And so to do that, I can have it be 2 minus t, so that's going to have my x's going in the right way. And so when t is equal to 2, I need my y value to be 3, and when t is equal to 0, I need it to be 0. So I think if I set it to be 3 has t, where my t's are going from 0 to 2, I think you can double check. If I plug in 0, I'm at 2, 0, so that's my point right there. If I plug in 2, I'm going to be at 0, comma 3 halves times 2 is going to give me 3. Yeah, so that's going to work out well. Okay, so our closed line integral, we're breaking it up into these 3 pieces. Okay, so let's figure out each of these. So for C1, I'll put my vectors over these. For C1, my parameterization is T0, so plugging that in for F, that's going to give me T squared, comma T, and I'm dotting with the derivative of T0 is going to be 1, 0, dt, going from 0 to 2, and so this is the integral of T squared from 0 to 2, dt, which gives me, what, t cubed over 3, so this is 8/3. So the second one looks like it's going to be a bit of a doozy. So let's skip and do the third one. We'll come back and do the second one last. So C3, this one is similarly nice to C1, except this one, my x's are all zeros and my y's are 3 minus t. And so we're going from 0 to 3, and then plugging this in to x squared, comma x plus y, is I'm going to have 0, comma 3 minus t, and then the derivative of the parameterization is going to be minus 1, is 0, comma minus 1 dt. And so this turns into 0 to 3 times t minus 3 dt. And so this is t squared over 2 minus 3t, going from 0 to 3, which gives me 9 halves minus 9. So that's minus 9 halves, right? So let's write this in, what we have. So we have that first one is 8/3. The last one is minus 9 halves. And then what about the middle one? So let's get some space in here. Okay, so for the middle one, our parameterization is 2 minus t to 3 halves t. So doing C2 f dot dr, and so our bounds are from 0 to 2. So x squared is going to be 2 minus t, quantity squared. And then x plus y is going to be 2 minus t plus 3 halves t. And so that's going to be 2 plus 1 half t. And then r prime is minus 1, 3 halves dt. And so doing the dot product, we get minus 2 minus t quantity squared plus 2 times 3 halves is 3 plus 1 half times 3 halves is going to be 3/4 t dt. So this minus 2 minus t squared, this is going to be minus 4 plus 4t minus t squared. And so we can simplify this. So minus 4 plus 3 is going to be minus 1, plus 4t plus 3/4 t, so it'd be 16 19/4. And then, oh, my bound is 0 to 2. And then, last but not least, minus t squared. And so plugging this in, so taking the integral now, so I'm going to have minus t plus 19 over 8 t squared minus t cubed over 3. And we're going from 0 to 2. Plugging 2 in here, I get minus 2 plus 19 over 8 times 4 is going to give me 19 halves. Minus, that should be over 3, minus 8 over 3. So 19 halves minus 2 is 19 halves minus 4 is 15 halves. And so this is 15 halves minus 8/3. And so then to get the full integral, we're going to add the first integral, which is 8/3, plus the second integral, which is 15 halves minus 8/3, plus the last integral, which is minus 9 halves. You see the 8/3 cancel each other off. 15 halves minus 9 halves is going to leave me with 6 halves, which is just 3. So, end of the day, this closed curve interval is just 3. Okay, so theorem. This is Green's theorem. So let's write that in. That's important. It's even in green. So for Green's theorem, we're going to be dealing with a line integral on a simple closed piecewise smooth positively oriented curve, like we just saw. And we're going to let R be the region enclosed by C. So if we have C is like this, going around counterclockwise to be positively oriented, R is going to be the region inside of C. So C is the curve, R is the space inside. Okay, then what Green's theorem says is really interesting, that if we take any continuous vector field, f, then the value of the integral along the closed curve on the outside is equivalent to this double integral on the region inside, where we go from our vector field function, f, capital F, and it gets transformed into, well, you take the partial of the y component in terms of x minus the partial of the f component in terms of y and integrate that over all of r, right? So the left-hand side, this is talking about a line integral in terms of c, whereas the right-hand side, this is talking about, if I can kind of copy out that shape, roughly like that, it's talking about a double integral over the region inside, right? And so this is one of the results that if you just looked at it, this seems inconceivable that this could be true. It seems pretty preposterous that you can swap out, on the left you have, this is a one-dimensional integral. I mean, it is curved, but it's still just a one-dimensional integral. At the end of the day, once you have parameterizations, it turns into just Calc 1 integrals versus, these double integrals that we've been working with before, which, are fundamentally different than one-dimensional integrals. And so this is quite surprising. So how does this work? Okay, so I've got a picture here of, a rough idea of the situation. This is a little bit simplified, but let's imagine our region looks like this. So C is the curve on the outside. You can see that it's positively oriented, and R is going to be on the curve on the inside. Okay, or R is the region on the inside. Okay. Now we know from line integrals that we can take any parameterization of C that we want, right? And that deep down what the line integral is telling us is you take your parameterization, you plug the parameterization into the vector field, dot it with the derivative of the parameterization, and then integrate between the endpoints, and that's going to give it to you. Okay. So looking at this, we see that inside on the right, there really are 2 points, 2 parts coming from the dot product. There's the part with the f component that's dotted with x prime, and then there's the part with the y component dotted with y prime. So we're going to break these up, and we're going to treat, this point, this whole integral right now, this is all in terms of t. So this is deep down just a regular Calc 1 integral. So it has an addition sign on the inside, so we can break this up and treat it as 2 separate integrals. So the first one we're going to deal with is for the x component. And so this f component one, it's going to be a bit annoying to write this out the whole time. And so we're going to use shorthand. We're going to call this our f component xy dx. So we're kind of removing the parameterization back out of it. This dx here is reminding us that if we have r of t is x of t, y of t, then dx is just the derivative of the x component dt. So this part right here we're calling dx, and so that's just lazy shorthand. This part right here is f with the parameterization removed. Okay. Okay, and so now we're going to take our curve and we're going to break this up into, same as we did in the example, we're going to break this up into 2 curves. We're going to break it up into a bottom curve going from left to right, and then a top curve coming back from right to left. Okay, and so the bottom curve plus the top curve is going to give us the whole integral. So the whole integral around C is equivalent to breaking it up between the top plus the bottom. Okay, so now let's look at this. And let's think about how we can actually parameterize these. So the way this is set up is this looks like we can think about the top part of the curve as being y is equal to some function of x, so it's top, let's call it t of x, and the bottom function we can think of as being defined by some curve y is equal to some other function, let's call it the bottom function, b of x. And then we've got these bounds, so we got to name these bounds. Let's name this one on the left, let's call that x equals L. And this bound on the right, let's call this x equals m. And so then we can think about the parameterization let's start with the bottom curve. We can think about the parameterization of the bottom curve. Since we have this written as x is equal to a function of y, we can actually parameterize this in terms of x. And so the parameterization is going to look like x comma b of x, where our x values are starting at L and going up to m. On the other hand, we can have, for our parameterization, we're going from m back to L, and so we can parameterize this similarly as x comma t of x, but now our bounds are backwards. We're starting with the bigger one, and then so we're starting at m and then going back to L. I don't want to put less than or equal to because that's not going to make sense because m is supposed to be bigger than L. But this is just to remind us that this is kind of parameterized backwards. Okay, that we're starting with the bigger value and going back to the smaller value. It's going to make sense once we put it into the integral. Okay, so that's kind of just reminding us of how we're parameterizing this, how we're thinking about this. Okay, so how can we parameterize the top? So we saw this before. The top is x comma t of x, and where we're going from m to L. The bottom is x comma b of x, and we're going from L to m. And so the top integral, I think we call it, let's call it c top of f of x, y, dx. So remember this dx is, well, in this case, our parameterization of the x component is x, and so when we take the derivative of x, it is just dx again. And so this literally is the derivative of that. And so we just have to plug these components in. And so for the top, we're starting at m, going to L, reminding ourselves that this is kind of backwards. And then for x, we plug in x. For y, we plug in t of x. And then we have dx. For the bottom, same as before, d of x is the derivative of the x component of our parameterization. And so this is an integral going from L to m of f of x, b of x, dx. Okay. And yeah, there we have them. Wrote them in the, flip the order, but it makes sense. Okay. Now we're going to go to the fact that these two are flipped from the way that we want them. So from Calc 1, how do we flip them back? Well, to flip them back, we need to change the sign. Okay, and so now we have our two bounds here matching. And so if our two bounds are matching, what can we do? We can pull them together as a single integral. Okay, and so this is what in total the x component is parameterized in terms of these two functions. Okay, so now let's look at let's go back at this and let's think about how we'd set up the double integral for the part connecting with f. Okay, so if you recall, if we focus on the part that's in terms of f, it was the partial of f divided by the partial of y in terms of a. Okay, now how would we integrate over this region? Well, this is a nice, we called it a type 1 region, where this makes it quite easy to integrate vertically, right? So if we take some x value in between, our y values, we're going to be integrating from y equals b of x to y equals t of x. And so we can have our y bounds go from b of x to t of x. And then what are the x values that we want to do these straight lines from? Well, we want to start at x equals L, and we want to keep going until x equals m. And so our x bounds here are going from L to m. And so then that's going to allow us to now write out the integral. And so this integral, so first we're going to integrate in terms of y from bx to tx of, so partial, so I want to think about how I want to write this. So another way to write the partial is f sub y with x and y plugged in, and so we're integrating y first, and then we're going to do the integral in terms of x. So the x values are going from L to m dx, and so now we're pretty. Okay. And so now if we're looking at this, well, if you notice in the inside integral, what are we integrating? Well, something that's a partial derivative in terms of y. And so if it's a partial derivative in terms of y, and then we integrate it back in terms of y, well, we're just going to be undoing that partial derivative, right? So taking a look and integrating this function, so if we're integrating, this is a partial derivative, but then integrating in terms of y, it's going to go from the partial of f just back to f. And our bounds here are from y equals b of x to t of x. And then if we plug those in, we get the integral from L to m of f of x comma t of x going in for y, minus f of x comma b of x going in for y dx. And this looks very familiar, except here the b's and the t's are flipped from what we had before. And so if the b's and the t's are flipped, this must be the negative of that contour integral that we got before. Okay, and so this is where the minus sign is popping up. Okay, so we have that. So this side is our double integral of partial of f dy dA over r is equal to minus f of x d of x. We can do the exact same argument with y's, except we'd be doing the region, we'd be thinking about it, breaking it up as x equals some function of y. It turns that in this case we don't have to, we have to flip the left-hand side rather than the right-hand side, and so we don't get a change of signs the same way. I don't want to go through the same thing because it would be pretty much the same thing. It would probably take about 10 minutes to do, and it's not really all that enlightening. We get all the ideas from the first one. But the other half of our original contour integral is going to give us the other part of Green's theorem. And so putting these together, in total, our total integral, we broke up into these two parts. Then we can swap these in with the double integrals that we calculated. And then, last but not least, since these are over the same region, we can put them back together, and this is Green's theorem. Okay, and so this is how we are able to swap from a line integral to a integral over a region. So in terms of how is Green's theorem actually used, well, it actually can be used either way. So sometimes Green's theorem, you might have a nasty line integral, and it makes sense to change it into a double integral. And other times you might have a double integral, and it makes it easier to swap it into a integral on a closed curve. Okay. But let's go back to the example we did at the beginning of this video, and let's go and think about how we would do this using Green's theorem. Okay, so again, remember the region here is this triangle. And so let's see, let's integrate over y first. And so if we're integrating over y, so this is from y equals 3 to x equals 2. So let's see, I think this is 3x plus 2y equals 6 gives me this line, so let's double check. If I plug in x equals 0, then y has to equal 3, and so that gives me this point. If I plug in that y equals 0, then x has to equal 2. So that gives me this point. So that is a nice version for there. And so then if we're going to integrate this in terms of y first, I need to solve for y. So 2y is equal to 6 minus 3x, and so y is equal to 3 minus 3 halves x. Okay, so that's good for the top. And so our y bounds starting on the x-axis, so that's 0, going up to 3 minus 3 halves x. And then our x bounds are just going from 0 to 2. Now our f function is x squared. Our g function is x plus y. So our double integral is, remember from Green's theorem, it is over the region of the partial of g in terms of x minus the partial of f in terms of y dA. So the partial of f in terms of y, there's no y's in there, so that's equal to 0. The partial of g in terms of x, so x plus y derivative in terms of x is just going to be 1. So we are just integrating r from, we're just integrating 1. And so plugging in the bounds, this is 0 to 2, 0 to 3 minus 3 halves x of dy dx. And so first integral, that's easy enough. That's going to be 3 minus 3 halves x dx. And then the outer integral is going to be 3x minus 3/4 x squared from 0 to 2. Plug this in. I get 6 minus 3/4 times 4 is 3. Gives me 3. And so I think you'll agree that this was quite a bit faster than breaking this up as the contour integral that we did in the beginning. And so that's the power and that's the fun of Green's theorem. In fact, we could have just noticed that if we're just integrating dA over r, then all we're trying to do is get the area of the triangle, and this is a triangle with height 3, base is 2, and so 1/2 times 3 times 2 is just going to give us 3. And so these are all much faster ways than actually integrating around the sides. That is all for this video. I will see you again soon.